So thank you very much for joining us for our second February edition of the Liftoff webinar series. Today we are happy to speak with ATC Materials on moldable RF materials as enabling technologies for hypersonic sensors and seekers. My name is Joe Steele. I'm the Senior Director of Communications and Legislative Affairs here with LIFT. Hypersonics is obviously important to the Department of Defense, one of the critical parts of their modernization priorities, and something we are taking a closer and closer look at with our team here at LIFT. So I want to thank everyone for taking the time to join us today and learn a little bit more about ATC, who was one of the recipients of a project through the Hypersonics Challenge that LIFT put out last year in coordination with the Department of Defense to solve a couple of problems related to hypersonics materials. And I think that that is something that the team from ATC will talk about today. I have a few housekeeping issues to speak to today before we get started and hand it off to ATC. First, everyone should be on mute. If you are not on mute, please go ahead and do so, but everyone should be muted. We are recording this presentation, so it'll be available on the LIFT website at lift.technology coming up later today, or certainly by tomorrow morning, so you can review this presentation or send it to folks who may not have been able to join us. And if you do have a question, we do have a question and answer session following the presentation. Please use the Q&A function at using the Zoom toolbar. Everyone's very familiar with Zoom and other technologies these days. Hopefully we'll get back to more normal activities here in the near future. In the meantime, use the Q&A function as opposed to the chat function. We'll do the Q&A afterwards. So thank you very much. My name is Joe Steele again. I do want to take a few minutes to tell you a little bit about LIFT. LIFT is a public-private partnership between academia, industry, and government, and we are one of 16 national manufacturing innovation institutes around the country. We are located in Detroit, Michigan, and our goal is to drive American manufacturing into the future through technology and talent development. And what does that mean? That means we want to be smarter about manufacturing because we know that on the manufacturing sector rests our economic security and resiliency. And the next region that tackles that first is going to come out ahead, and we want that to be the USA. So what does smarter manufacturing mean? Well, we've nailed it down to this equation, the connection between materials, processes, systems, and talent that runs underneath all of those. Put all those together, and then we're looking at manufacturing holistically, and we want to make sure that we are doing that. So we're not being siloed, looking at just materials without understanding how they need to be processed, without understanding the system it's going to end up to at the very end of the process, and I mentioned talent that is required to go with all of those. Want to make sure the talent pipeline is robust and healthy. So we do that with two programs at LIFT: Leading Innovations for Tomorrow, our technology program; Learning Innovations for Tomorrow, our talent program. I'll touch on both of those briefly. Leading Innovations for Tomorrow, the talent program, again, about connecting materials, processes, and systems. You can see we run all the way from digital side, the virtual side at ICME, Integrated Computational Materials Engineering, taking a look at materials and the virtual space. How do we better predict how they'll be processed? How do we know how they're going to react, particularly as we're developing new processes, additive, things like that? How do we know that this material is exactly where we want to be? Agile and smarter manufacturing, again, these new processes. How can we change the way we're processing things to be more agile, more nimble, and smarter about how we're going about things? Advanced alloy process development, back into our metallurgy history, looking at advanced alloys and processing them, and finally, how do they all put those things together? How do we join these materials going forward? So deeper look into some of those pillars of technology that is just referenced. You'll see hypersonics listed on their advanced alloy process development. We are certainly keen on working with hypersonics, but we would work on all of these through our ecosystem as well. So questions about these, I won't quiz you on these now, but if you have questions, please reach out to us directly, and we'd be happy to share information about how you can get involved with Lift. On the talent side of the equation, again, it is still about innovation here, but these are innovations around new learning tools, pathways, and venues. We're looking at things of how do we better prepare the workforce of the future? How can we marry the educational aspects with our technology to make sure that the students are better prepared to enter the workforce with the knowledge, skills, and abilities the industry is looking for? So starts with our Ignite Mastering Manufacturing curriculum. That is a 3-year curriculum for high school students, if that's foundational to them, starting with material science and introductions to manufacturing, getting into advanced manufacturing systems. We run that out of the Lift Learning Lab here in Detroit, pre-COVID certainly, but there are virtual online aspects of that curriculum that students are still participating in, and we're hoping to get the students back in our facility full-time here in the near future. In the meantime, Ignite is rolling out across the country. It is available out in 11 different states now. So we're working with high schools around the country to get this curriculum out there. So happy to work with folks in industry to see how we can roll that out, faster. The Learning Lab itself is a unique lab. It is perched above the high bay here in our Detroit facility. Again, students come in here and learn kind of by osmosis. They come in and we're able to look down and see all of our technicians at work and our ecosystem at work there. And then there's 2 programs that we have that we're preparing students for the workforce that are available right now. Our Lift certified programs, offering credentialing programs or credentialing opportunities in CNC operations, robotics, welding, industrial technology, maintenance. And then Operation Next is another program that is available in different areas of the country. Started as a pilot for active duty service members before they leave the service. 6 months prior to leaving the service, give them the opportunity to earn a credential in one of those 4 majors so they can hit the ground running with their civilian career. That program, after successfully being piloted at Fort Campbell, Kentucky, has been expanded to the National Guard and Reserve in Michigan, National Guard and Reserve in Wisconsin, the National Guard and Reserve in Florida, and their spouses, which is great because those spouses are often underemployed. And then we also expanded to the Hampton Roads region of Virginia for those active members and their spouses as well. And so we're looking for future expansions. So stay tuned to your emails and the news coming up with Operation Next. That is continuing to grow across the country and one of the programs we are most proud of. Finally, I mentioned we are a public-private partnership. We're also a membership-based organization. So what do you earn by becoming a member? Well, all the things you see on the screen here. We are a trusted advisor, giving folks the best advice possible, both from our in-house experts as well as our ecosystem experts on how people can turn the corner and become smarter in their manufacturing. Technology accelerator, as I mentioned, we're taking technology from good idea to commercialization across the valley of death. We are not in competition with our industry members. We cannot be in competition with our industry members as a public-private partnership nonprofit, but we help accelerate those technologies and move them across from idea to commercialization. We're a technology showcase. Our 100,000 square foot facility here in Detroit. We're happy to show people around, slowly, hopefully getting back to normal here and inviting people in. But if you're in the Detroit area, please give us a call. We'd be happy to show you around. We are a connector and a convener. That's why we're all here today. So thank you very much for taking the time today, trying to bring the best and brightest minds together to talk about the future of manufacturing. A talent developer, as I mentioned, we are developing the talent of the future as well as the talent of today. So would love to partner with our industry members and industry partners on that. And finally, we are a government partner. The federal government can be unruly, bureaucratic to work with, but we are a conduit to help do so, particularly for small to medium-sized manufacturers. It can be tricky, but at things like the Hypersonics Challenge that I mentioned earlier, we're able to get smaller companies involved. So invite you to join us. You can give us a call. You can take a look on our website. You can send us the email. You can follow us on our social channels. Invite you to do all of that and learn more about us at Lift. So in the meantime, you were here to hear from ATC and their team. So I'm going to stop sharing my screen and hand it off to Matt so he can begin his presentation. So Matt, the show is yours, my friend.
Great, thanks, Joe. I think we should be live now.
Yep, you're all set.
Get my screen set up. Okay, great. Well, thanks, Joe. Thanks for the opportunity here, and thanks everyone for joining. My name is Matt Replenovich with ATC, and I'd like to just give you a little bit of an introduction to ATC, and then most specifically, the topic today will be RF materials for extreme environments, and we'll tie that in with the work that we're doing with the LIFT Hypersonics Challenge. There we go. So this is the plan for today. So we'll offer just an introduction to ATC, who we are, what we do in some of the areas and markets that we serve. One of those areas is ATC Armor. That's a big part of our company. So we'd like to offer just a kind of a quick review of our armor and some of the work that we're doing in that area. And then the other half is RF materials. We have a few different products in that category. I'll introduce a few of those. But we'll focus on material that we call RIPS, and that's the one that has interest in hypersonics, and that's the one that's aligned with the program that we're working with LIFT right now. So we wanted to make sure that we kind of give a broad overview of ATC and what some of our capabilities are, but then try to keep the focus pretty narrow to the work that we're doing with LIFT right now. And there should be plenty of time for comments and questions at the end. So to get going, ATC. So we're a small business, and as mentioned, armor and RF materials are our two distinct product groups, and we also have two locations. So headquarters is Westlake, Ohio. That's where I am. So we're just outside of Cleveland, not too far from LIFT in Detroit for some of the programs that we're working there. That's our headquarters. It's where we do our modeling and simulation. We have our computer cluster for those operations. It's also where we do all of our armor simulation and manufacturing. The other half of the business is located in Flagstaff, Arizona, and that is the materials R&D center. So all of the new materials are developed there, and all the production of the current materials happens out there, and that is where the hypersonics focus is. Our primary customer is the DoD, and a lot of that is just because they're driving the material development in these niche markets that we're in. And we are a small business, so we do have limited resources. And although there are some different commercial applications that we do offer products and services for, right now we're really busy and kind of focusing on the DoD customers. And as we grow, we can move into some of those other areas. So just kind of a big picture of ATC and what we do. So products, as I mentioned, is armor systems and RF materials. So those armor systems, the focus is on insensitive munitions, and I'll go through that in a little bit of detail in the next couple slides, but it's multi-hit structural armor with a perforated steel strike plate featured in many of them. The other half of the business is RF materials, radio frequency materials that are designed specifically for their dielectric properties and specifically for some extreme environments, elevated temperatures, things like that. RIPS is the one that we'll focus on today, but we also have some other composite materials for lower temperatures, radomes, things like that. And some of those materials have some roots in thermal protection, and then some opportunities in some new areas like directed energy protection. So is there a way to apply a film of a material over a substrate to protect a UAV against laser weapons or something like that? These are some emerging areas that we're looking at. Not a core business yet, but some areas that they're moving into, and it just sort of highlights our interest in materials design. So the services, as mentioned, material design, mostly dielectrics, but also all of our materials are moldable to net shape, and we'll get into that a little bit later. Armor design, big part of the business. Again, we have a few slides on that, but that's modeling and simulation for material models, projectile models, energetic reaction models, things that allow us to design armor architectures for specific uses. And then again, the modeling as a service as well as manufacturing. We do have some specialty equipment that allows us to make these different things, including a 5-axis water jet, and we have some basic composite processing equipment as well. To help us along, we do have a number of relationships with some other businesses that are adjacent to our interest. One of those is a team of propellant engineers that worked for some, let's say, major primes. So we can get rocket motors manufactured for us when we need to do surrogate testing. And then they're also useful for just other ablative test or non-ablative material testing, using the rocket motors, developing throats and nozzles, things like that. And then weapon system modeling. So we're primarily interested in in armor to protect a weapon system. But some of the teams that we work with to help us out also do some lethality models and energetic reaction models, which are useful to support some of the designs that we work on. And then the applications, number one is insensitive munitions for armor. That's what I'll focus on as a brief introduction today. But vehicle armor, structures, shields, any sort of armor is possible, but we do focus on specifically the protection of munitions. And then in our material side, the focus is radomes, RF windows, conformal antennas. That's what we use our dielectric materials for. But as I mentioned, sort of entering into the commercial market, industrial sensors and oil and gas, chemical processing, other just harsh environments where you need a dielectric material that can withstand that extreme environment. That's what our materials are great for. And communication, some sort of satellites and other communication systems. Our dielectric materials as waveguides and phased array sensors, things like that, have found some specific uses in the past. So that's kind of a big picture of what we do as a materials company. And it's perhaps a little bit tricky on how did a small business like us get involved in these sort of two disparate areas of dielectric materials and armor. And this is a very simplified cartoon of how it happened, but the original intent was a injection moldable high temperature material. And there was a few different potential use cases for it. Because of our location near NASA, we had some exposure to some of the engineers there, and it turned into some thermal protection systems, things sort of reminiscent of space shuttle tiles, at which point some RF testing was done, which led to thoughts about radomes and different materials like that. And that's where the original term hot blocks sort of evolved into. That's our composite dielectric material. Good for some lower temperatures, 350, 400 degrees C. What if we need to go hotter? And that's where the silicon nitride came about. So maintaining the injection moldability, maintaining the dielectric properties, but for elevated temperatures. And that's what I'll focus on today. But of course, working in ceramics and then talking about radomes and radomes that may have rain impact testing or different things like this. At some point, somebody noticed it was pretty tough and said, hey, have you ever shot that? And that's, I think, typically the way a lot of people get involved with armor. And that's certainly our story. In early cases where early armor systems were body armor, we actually performed really well with some early body armor designs, but we weren't going to take on the companies that could beat us at scale. So when some of the folks that were looking at these other materials for missiles said, hey, our missiles need to be protected when they're being transported or when they're being stored, can you design armor for that? And that's really where the IM armor came about, the insensitive munitions armor came about. And then, of course, from there, looking at armoring some different things. So what we've ended up with are sort of two different product families that really have nothing to do with each other and nothing to do with what ATC was originally started as, but really work out nice for us because they are complementary in that we do deal with a lot of the same customers, and a lot of the techniques and the models and simulations that we've developed for one can be sort of applied as expertise towards the other. So that's just a little bit of a history on how we got involved in these two totally different areas. So I'll give a quick introduction to the armor part here because it is a big part of our business. Insensitive munitions, I mentioned that it's high threat armor. So this is high energy. The two NATO standards are there, 50/50, 350 caliber rounds impacting within a 2-inch diameter circle, 100 millisecond intervals. The other one is a single 14.3 millimeter fragment simulating projectile at 8,300 feet per second. And if you're not familiar with ballistics, a 50 caliber might travel around 2,700, 2,800 feet per second. Handgun maybe 16 to 1,800 feet per second, and this fragment simulating projectile at 8,300 feet per second. So extremely fast, meant to simulate the effects of shrapnel, of artillery exploding nearby, or sympathetic detonation. If a missile next to your missile explodes, detonates, that debris headed towards a series of them in storage. That's what that's intended to store, and that's represented by this little cylinder here that just travels really quickly. So that's kind of the threat. Why is it important? So insensitive munitions really came about from some Navy disasters where they have a lot of munitions in close quarters. that can be a real dangerous situation if something were to happen to one of them. The official DoD directive labels it unplanned environmental stimuli. There's a number of different versions of that in terms of fire, sympathetic detonation, but really the two that we're focused on are bullet impact and fragment impact. So that's, again, the 5050 as well as that fragment simulating projectile. And it's important because missiles and munitions are typically shipped and stored without protection. So they might be in a box, they might be in a canister, they might be in their launch tube, but none of those things are armored. So it means that they're sensitive to potential attacks. And it can be a real dangerous situation because, of course, in the case of the Navy, you have lots of munitions in close quarters with the sailors. And in any situation, you want to make sure that the asset is ready to use when it's necessary. And so these things are typically graded in their response 1 to 6. So what that means is a grade of 1 is a prompt detonation. So in the case of a fragment impact, the fragment hits it, it detonates. That's a type 1 reaction. Type 6 reaction means the asset is not affected. So that you can consider that as nothing passes through the armor. The asset is okay. Type 5 is a slow burn. It's generally means that the asset may be compromised, but it hasn't exploded. So still not a good situation, but generally safer for anybody that may be nearby. So you have a series of potential impacts that are then graded 1 to 6 based on the response of the energetics. So energetics can mean a number of different things. This is a picture of a standard missile. It generally in our world means propellant and rocket motors, because on something like this, it's all propellant to get a kinetic warhead to intercept a target. So there is not I should say that differently, to get a kinetic kill vehicle to hit a target, there's no warhead. So there's no explosives in this. We're only worried about the rocket motor. So how do you prevent a rocket motor? How do you make a rocket motor safe? Historically, there's been a lot of work in reformulating the propellants. That generally means loss of performance. So you decrease performance in the name of safety. What we offer is shipping containers, launch tubes, and canisters that are armored that allow any propellant to be in there at any performance value, but still can provide the safety. So the way that you get there is with modeling and simulation. That's the tools that we have developed to make this happen. And this is an example of a armor system that's been impacted with a fragment. And the critical part here is we're going after a type 5 with these designs. So what does that mean? A type 6 is really easy to characterize. It means that if you shoot it, nothing comes through the backside. That's something that you can test empirically very easily. But a type 5 solution, you can save 50, 60, 70% of the weight by allowing some of the debris to pass through the armor and impact the asset. But how do you know what kind of debris field is acceptable? So in this area here, how do you know what kind of debris field is acceptable that'll be at a threshold below detonation? So that's what this half circle represents here. That's propellant of a rocket motor. So what we can do is we can simulate the projectile, the armor, the debris field, and the energetic reaction model to develop a armor system that controls the debris field or controls that projectile in such a way that you may sacrifice the asset, but the damage is below threshold for ignition of the propellant. So that's a real quick view of sort of what the goals are. And then the way that we get there, this is just one example, but this is an example of a 50 caliber projectile that's been modeled to identify what's necessary to fracture the core. So you want to strip the jacket off of it because that reduces mass. You want to fracture the core because now you're displacing the impact and the energy across a broader area. And to do that, you have to actually develop material models that exist sort of at strain rates beyond what's typically done for most steels and for most engineering services. And the result here is this side-by-side that we have in the black and white here. So the left version of it is an orthogonal picture, top and side view of a 50 cal as it passes through armor. And the right, the slightly grainier version, is an actual X-ray of the event. So you can see sort of the fidelity that is available in terms of both identifying the fragmentation, the mass of the pieces, the velocity of the pieces that allows us to design these armor systems. So what is it used for? A bunch of different versions. The one that we've recently worked on is a Type 6 armor system for missile defense, and that was a sole source contract for us to produce that. And that was a modular system that allowed them to move their missiles safely. But we also worked on these Type 5 systems. So those are appliques or inserts for existing containers and missile launchers. And that includes an applique that might go on a mobile missile launcher or inserts into shipping containers. What we're really working on is, since our armor is structural, it's self-supporting, we'd like to manufacture ISO containers and other things out of our armor that protect whatever goes inside of it. So that's a quick view of Incentive Munition and half of the business here at ATC. But I think it's important just to kind of give a picture of what we do and kind of get a feel for the other half of the business beyond our RF materials. So this is the area that we kind of want to spend some time with here today. RF materials, radio frequency materials. So we make a family of products that are designed to have specific dielectric properties to be used in sensors and seekers, antennas, and other similar systems. The goal for us is a predictable and repeatable dielectric performance. So what does that mean? That as from low temperatures up to the service temperature, that the dielectric remains as stable as possible, the dielectric constant, the dielectric properties as stable as possible, but they're also repeatable, so that if you cycle from cold to hot multiple times, both on the way up and on the way down, it's going to trace the same line so that the system designers know the behavior of the material throughout all different environments that it might be in. And although we are a material development company, we do create these custom materials for our customers. We like to provide finished components because a big portion of the performance of the material is the way that it's manufactured. So rather than supplying a material for someone else to turn into a component, we take all of that in-house and we deliver a component that's ready for use or ready for integration in your system. These are the two main families of materials that we have. So I mentioned, hot blocks is a name that traces back to the original intent of American technical coatings, though it has evolved significantly since then. And today it's a composite dielectric that we can tune at the time of manufacture to a specific properties for your application. It's also unique that it's designed to have a coefficient of thermal expansion matched with aluminum, and it's moldable to net shape. So what does that mean? Number one, the CTE match means we can mold it in inexpensive aluminum molds. So that helps the manufacturing process, but it also means that we can co-mold it into aluminum housings or aluminum waveguides. So the picture in the top right, it's about an inch or 30 millimeters on a side. And those four little antenna windows there are the hot blocks material that is molded into the aluminum. So versus some traditional or alternate materials where the aluminum might be honed, the material might be machined to a specific or to fit, and then it's pressed in there. We can just take the aluminum, mold our material directly into it, and it's ready to go. It also then is going to maintain that interference fit throughout any temperature cycles, so it's not going to crack if it gets cold, and it's not going to fall out if it gets hot. This is a great application for the material. It can also, we've manufactured some different hemispheres and radome shapes from baseball, softball size, things like that. The other material, and this is where I've spent most of the time today, is our material, which we call RIPS. It's a silicon nitride version, and that's for elevated temperatures, higher temperatures, where hot blocks is good to 350 or 400 degrees C for short use. RIPS is a silicon nitride, so it's stable to 1400 degrees. And this is what's caught the interest of the hypersonics community and allows us to manufacture the windows for the sensors and seekers on these vehicles that experience the significant aerothermal heating and other extreme environmental effects during their Mach 5 or greater flight. So hypersonics, just kind of as an introduction here, there's a lot of I mean, it's a big interest now, of course. And one of the bigger challenges is to ramp up production of these new materials that meet the needs of the hypersonic industry. So I think the important thing to remember here is that these materials don't already exist. And so there's not necessarily competitive materials from a standpoint of displacing incumbents, but rather just it's a race to see who can get qualified first. And there's a lot of focus on structural materials, and certainly it makes sense. We have to develop the propulsion systems, and we have to develop the vehicles that can achieve these flight profiles. But we also need RF materials to allow for the communication and allow for guidance. So again, repeatable, low loss dielectric performance is necessary, but they also, of course, have to endure the thermal shock and the maximum use temperatures and survive the flight conditions, which is mechanical strength, rain impact, things like this. And certainly one of the key things, which is often left to last, but reliable manufacture. So just because you proved you can make it once, or you can make a small version of it, the DoD, of course, needs to know that they can select you as a supplier and know that you'll be able to deliver for not just the prototypes, but the transition to production. So it kind of is an example of what's out there in hypersonics. The US has nothing fielded right now. A number of programs are in development. A number of programs have been flight tested with various degrees of success. Those include some scramjet air breathing systems, as well as boost glide vehicles, which sort of rocket assist and then glide into their target. There's also a couple of different gun launch options out there, including the Navy's hypervelocity projectile, which does have or could have, let's say, some windows in it for targeting. And certainly the US has their own personal interest in doing this, but there are some hypersonic capabilities, hypersonic in quotes, just because some of these things certainly have not been validated, but China, Russia have some fielded units, and the rest of the world also working on some opportunities to field hypersonic vehicles. So looking here, RF materials for hypersonics. I mentioned, there's no state of the art. There are no hypersonic vehicles currently flying, so there are no incumbent materials. But one of the materials that's been identified as a likely candidate is silicon nitride with controlled porosity, because that's going to give it some unique properties that will enable it to be useful in these situations. So this chart here is a bit complicated, but intent is that the y-axis here is material strength, x is maximum service temperature. So we need to be hotter than, let's say, 1200 degrees and greater than 150, 180 megapascals. So this top quadrant is really the materials you have to select from that'll just survive the flight environment. But now you also have to pick one that has dielectric properties that your antennas can see through and your sensors and seekers can receive and transmit in through. So RIPS does exist up here, and this is a pretty small playing field of materials and market, which is why a small company like us can really find a spot for ourselves here. So RIPS, I've said RIPS a few times. What is RIPS? It's a DoD approved belabored acronym of reduced density injection moldable pressureless sintered silicon nitride. So that describes the material and how it's made. It's designed specifically for dielectric at high temperatures. And the way we get there is it's molded to net shape. So it's a simpler manufacture process than a traditional sintered silicon nitride. And for final products, it's better yield and reduced cost compared to billets that need to be machined to shape. Controlled uniform porosity, that's how we get there. That's what allows the dielectric properties as well as the thermal shock tolerance, and then mechanical survivability. So this is just a kind of a quick thing here without giving away all of the information that we've been, that's been sent to us, but dielectric has to be under 4.5, strength greater than 185 at temperature, and a max use of 12 to 1400 degrees C. And certainly our material meets or exceeds all of those different targets from hypersonics community. Looking at some of the competition here. So this is us, RIPS in pink or red here. compared to a fully dense sintered silicon nitride. So strength is reduced significantly, but still shows enough to survive. Perhaps not as a leading edge, but certainly works well for the RF elements that are on any of these vehicles. But the key thing is our dielectric constant is half of a fully dense silicon nitride, which means that those sensors can operate effectively. And then compared to some of the other materials which may have previously existed on other missile systems, like a slip cast fused silica, the dielectric constant is similar, but the big difference is increased strength. So where the slip cast fused silica as a monolithic material has perhaps left a bad taste in some people's, a bad taste for some people because of prior poor performance, we think we found the right spot of strength and dielectric performance in monolithic materials. And certainly there are some competitive future materials of CMCs and carbon and different things like this, but they don't hit the same spot that RIPS does. And there's also some concerns about the composite materials and the variable performance if they're not made as homogeneous as they could be. So versus a monolithic material. So why RIPS and what makes us interesting? So mention the performance. Cost is also a big part of it. It's moldable to near net shape. So we'll talk about that in the next slide, but that means that for production parts, it's much cheaper to manufacture a RIPS part than it is conventional materials. And design, because we can mold it to net shape, we can make some really complex shapes. And we can also do some work on surface finish that could provide some unique performance attributes just through the finish of the part, as well as some really complicated things like mold and place threads for attachment and some other pieces like this that would allow the ease integration of components made out of RIPS. So looking at this one here is kind of an overview of the manufacture process, and this is really what's unique. Everything is done on conventional equipment, and it's done with readily available materials. So it's just the recipe and the process that is unique. So formulation, we do have our preformed material, which allows us the viscosity to mold it to net shape. That molding process is really what's going to influence the material properties. So it can be again, molded sort of in conventional tooling on a injection mold, transfer mold machine. And then the key part then is what we would then call conversion. So burnout might be a traditional term, but we have very little mass loss because of the formulation that we use. And this means that the part doesn't shrink much during this process. And it means that it is very dimensionally stable during this process. So that's what allows us to mold a green part and then carry it through to through conversion and sintering and maintain the shape. And this is also where that controlled uniform porosity is going to be created. Sintering is pretty conventional. And then machining, depending on the part, there may be some final machining that's necessary, but generally speaking, surface finish and everything else is good enough for use right after sintering. So that eliminates a lot of complexity. And as an example, we did work in Army prototype, where about 50% of the cost of the Army prototype conventionally was machining. So 50% of the cost was buying the billet and 50% was machining the billet. And we can just make the part. It is the molding is the key to the performance, but it also affords the manufacturability. Here's a couple generic examples of some shapes and geometries that we've manufactured. So thin wall radomes with complex curves, conic sections or RF windows. So if we're not making the whole radome, we could anticipate that this frustrum is made out of a different material, and we would make a compound curve that can be integrated in it as an RF window. This sort of third picture over is actually pretty small. It's maybe 4 inches tall, a hollow cone, but fully closed. You can see at the top, that's the end gate. So that'd be the only piece of machining that's required to shape the tip. And then on the right, just a couple of cartoons of a real simple, or the lower right is a sort of a cartoon of what the mold could look like. And then we actually have a mold image on the top where we have an outer mold line and then a mandrel which fits into it. The space between, of course, is the part, and then can use a few different geometries of gating to introduce the material, but a traditional manufacture or molding process really there to get to any of these shapes. I mentioned the modeling and simulation that we do for armor. We also do quite a bit of that in our material preparation. So because these are complex and high value parts, there's a significant benefit in predicting their behavior before you manufacture them. And so that can be used certainly also to predict the manufacturability of the part. So on the left, the orange image there represents a part in our furnace, and we can take or in a furnace. So we can take a look at the temperature gradients within the furnace to identify the heating effects on the part. And then the parabola on the right represents the temperature deviation from the surface to the center line of the bulk of a part. And then you have and that allows you, if you know the constituent material properties, so the coefficient of thermal expansion, for example, you can identify the internal stresses on a part before you make it and develop a sintering schedule that will keep those stresses under threshold to prevent cracks or fractures during the sintering process. So that's just sort of an example of how we can use some computational tools to help not only develop materials, but to develop processes to help us manufacture those materials better. Should mention the project that we're working with LIFT right now. So official title is Net Shape or Near Net Shape Manufacture of RF Materials for Hypersonics. But essentially what we're going to take a look at in this program, it's a directed study on the effects of molding on the finished part. So because our process for manufacture is a little different, we do have a well-characterized material, but we're going to take a look specifically at the surface effects versus the bulk material properties. So we can use those surface effects to manipulate the material in an advantageous way to create a grain alignment, structure alignment, different densities, things like this. But if we're not trying to do that, are there any differences between the surface microstructure and the bulk material microstructure of the material? The image on screen there is one as molded and one molded and machined part. But we're going to make, in this case, these are ASTM flexure bars. And we're going to work with Ohio State and University of Dayton to do some material characterization and then mechanical testing of the materials, and then analysis after the fact so that we can begin to correlate any of the microstructure differences with performance differences and understand what contributes to the microstructures that we can increase performance or maintain a more consistent performance throughout lots and batches of material. And so that started last fall, or I guess November or so. So we got a little, we're really getting into it now and have a little bit of time left to go on that LIFT program. And this is sort of the last slide here, just to indicate some of the people that we're working with and the programs that we're on. So of course, we mentioned LIFT. We have Army, Navy, or Navy, Air Force, and Army in order there. SBIRs and STTRs to focus on material enhancement. So what's the next version of RIPS going to look like? To focus on material characterization and testing and prototype development. We also then have multi-service support for an OSD Mantech program to increase manufacturability of the materials so that we can better serve our DoD customers. And then work with a number of different institutions and labs to do testing and analysis on it. We have a great relationship here in Ohio with Ohio State, University of Dayton. Worked at the Lemmel lab for some high heat flux testing, flown on the space station 3 times. And the top one on the right corner is the University Consortium for Applied Hypersonics, UCA. I imagine many of you are familiar with that. We are also members of it. So certainly if there are any future proposals, programs, or otherwise coming up that might benefit from RF materials, we'd love to talk about it. And finally, that's my information. So if there's anything on our materials that you're interested in, please contact me. My cell is on there, call or text that, as well as my email. And I know we touched on a bunch of other things on our lower temperature RF materials, as well as the armor. Feel free to reach out on that as well. We'd love to talk about it. If enough of you are interested, Joe, maybe you can give us another time. We'll come back and talk about armor. But that was hopefully just a good overview of ATC, as well as a little more in depth on our material for hypersonics.
Awesome. Thank you very much, Matt. And that's a lot of information, and everyone listening and watching in today can certainly understand why ATC is part of the LIFT membership and LIFT ecosystem now, singing from the same song sheet on a lot of things that we are working on in terms of materials development. Glad to have them as part of the partnership. So please reach out to Matt with any additional questions or comments, or want to learn more about how you can work with them. And we do have a little bit of time for a Q&A here. So if you do have a question, please use the Q&A function on the Zoom toolbar there, and we can get a few questions and answers in. But Matt, I'm glad you talked about hypersonics broadly in terms of what it is and what is going on in the rest of the world, actually. So I guess I have a big broad question. I'm not sure if it's fair or unfair to ask, but I'm going to ask it anyways, which is, you'd highlighted where the U.S. is in terms of it being a priority, and where we are, at least in terms of getting vehicles made, materials developed for hypersonics, and where some of the other folks in the rest of the world are. What is it going to take? How far behind are we in terms of that process, and having materials with the ability to move as fast as we need them to for hypersonics?
Yeah, well, I will say that is an unfair question. So where we exist in this, I guess in our involvement with hypersonics is very narrow, because we're RF materials, and that's what we do, and that's what we focus on. And certainly also because of that, we are firewalled from much of the other information. But from our standpoint, we know that the majority of research in hypersonics has been just making something that can get up to speed and stay together. Exactly. So it's all been in propulsion, and it's all been in high temperature materials for leading edges, vehicle skins, and vehicle structures. Mm-hmm. We know there's a ton of work there. We also know there's been a number of flight tests with varying degrees of success on that. To really identify where we're at is difficult, but also, I put in parentheses, and just based on the research, there's claims of other fielded units internationally. I don't know, I'm sure plenty of people do know, but we don't know if anybody, how far ahead or behind we are. Right. But I will say that, the guidance is kind of the last thing. The vehicles need to fly before they need to see where they're going. And so we're really fighting hard to make certain that we're ready when the time comes, and that we can be there to integrate into these systems that are currently being designed.
Well, I appreciate you answering that question as best you could. I did say it might be unfair, so but we do know that it is a top priority of the DoD for a reason, right? And because we need to get there, and whether your scope is narrow or broad, we need to get there, and it takes organizations like yourself to help us get there, and hopefully working with us here at LIFT, we're able to bring those groups together and organizations together to move the needle. So we have a couple of other questions coming in. Are you interested in extreme ZTE materials, including some of the new ceramics that are out there, if you're familiar with silicon, aluminum, etc.?
Yeah, I think so. From our standpoint, as kind of mentioned, is that it's easy to get distracted by every shiny thing that you see, and so there's all sorts of interesting things out there that we certainly need to keep apprised of, and we want to know who's doing what and how it relates to where we're at. We're pretty busy in the narrow market that we're in now, and we really have to stay focused on it. But for anybody that is has some other materials that they think are complementary, we have to, of course, we're interested in learning about them, but in terms of where we're at now, we have to focus on developing our material to prove that I think we've proved that it meets the performance requirements, and we really have to work hard to demonstrate that it meets the availability requirements. And that's kind of our main focus right now.
Mm-hmm. Mm-hmm. What about the question here about stopping DEW microwave energy? Any testing or ability to in that scope?
Yeah, so this was one of these things that just came up on a hunch. We, without going into all the details, we had some inclination that one of our materials might be pretty good at providing directed energy protection of substrates. And knowing that there's a number of people working on counter UAV weapons, we sort of were interested in, is there such a thing as counter UAV? So we did some very simple tests when as part of another program, so sort of end of the day test when we were doing high heat flux and high enthalpy testing. We did some guesses at directed energy and came up with some interesting results. The issue that we have is we don't know what the threats are, and no one has told us specifically, what the watts per meter squared is or for how long. But we do know that our material has been purchased by some other groups to test specifically for that. So the answer is we'd love to know more. We know that we are manufacturing material for other people to test, but we do not have the results. So it's kind of that tricky situation of some government entities have expressed interest, but so far we haven't crossed the threshold that anybody has told us precisely what they're doing, other than we continue to supply samples. So if anybody has more information, or has the potential to work together, we'd love to speak with you. But right now, that was one of those things that's when resources become available, we'll spend some more time on it. But right now, we're just providing samples for other people to take a look at.
Got it. And again, you can reach out to Matt. His information is on the screen now, and you have time for a couple more questions if there are any that are out there. Matt, you talked early on about coming up with new materials, really, and testing them virtually, and that is an area that I touched on in terms of LIFT's work with some of the material scientists that we have on our team, as well as our ecosystem. Just can you talk about the importance that plays in terms of developing new materials? We don't know what we don't know in terms of what we need. I guess to move some of these ideas that we have forward and coming up with new materials. We talked about the idea of connecting materials and process. Is that an area that you're working on as well?
Yeah, I mean, I think for us, and I would anticipate this is similar for many companies, but especially the small businesses, is the number one thing that a company needs is a customer, right? And we can invent all kinds of materials that do interesting things, but that's not the correct path to go out there and then figure out who wants it. So the number one thing that we need to do is identify what the gaps are and what is required from the customer. And when DoD is your primary customer, that's a difficult challenge. But certainly when it does come in, we're focused on right now increasing manufacturability of our materials, but now looking at material enhancement. So then just to stay with RIPS, for example, how can we make it a little bit stronger, or how can we change the thermal properties? And does it make sense to have in plane versus through plane thermal properties which are divergent, or maybe not divergent, just different? So there's a ton of opportunity to do development work. And again, we can use simulation to offer predictive values of what is possible. And then in our lab, we can develop some of these materials and try to show that we can achieve it. But the number one thing that we have to do is get a voice of the customer to say, if you can make this, we're interested in it, or here's the shortfall in what you have now. And that's, I don't want to say that's the biggest challenge, because certainly making the material is tough enough, but that is a big challenge, is to make certain that you understand if your material doesn't pass a test, getting the feedback so that you can make it better. And also, if we're chasing a dielectric of 4, maybe the answer is keep it at 4.7, but make it a little stronger. And having those dialogues, I think, is as critical to the actual work that's done.
Right, the difference between finding a solution in search of a problem versus finding the problem first and developing a solution for it. Correct. So yeah. Has your material been used in hybrid applications where it's been encapsulated into a casting at all?
I don't think so, or at least not in the way that I envisioned the question. So we can, as mentioned, the hot blocks material can be molded into aluminum, though there are some limitations, of course, temperature-wise in both what the hot blocks or the aluminum can withstand. In terms of the RIPS material, no, but it has been, I guess I'd say no, but without knowing more specifically what you're interested in, I can't confirm, but that was sort of the intent of the genesis of ATC, was to use a material which again has nothing to do with anything that we do now. That could be an injection moldable material for a cheap way to make molds for castings.
Got it. Understood. Hey, I appreciate that, and Tom, I think we can follow up offline afterwards, as we are running out of time. So so I appreciate Matt. I appreciate your membership. Appreciate your presentation. Appreciate you working with us on solving this, helping solve this this top priority for the DoD. So so thank you very much for spending time with us today, and thank everyone for joining us today, learning a little bit more about ATC and the work that they are doing. So in the meantime, reach out to Lyft here with any additional questions, comments, social channels. Reach out to Matt as well. As mentioned, the presentation will be posted up on our website a little bit later today, or by tomorrow morning. So Matt, thank you again. Appreciate it.
Yep. Thanks, Joe.
Awesome. And yeah, thank you everyone for joining. We'll talk to you next time. We'll be coming up in March with AddUp Solutions. Will be joining us to talk about their additive technologies. So thank you very much, and we'll talk to you soon. Thanks all.
All right. Thank you.